2 math presentations. We're going to do a biology presentation, and we're going to finish with 3 math presentations. Students, note, down there on the bottom there, all of your presentations are open on the desktop in order. So, without further ado.
Chris, Michael, Ludfor, and Fernando.
Hello and good morning, everyone. Thank you for joining us. Today we will be presenting a basic model of population representation between lions and gazelles and how it varies over time. Our methods are comprised of derivatives, which is a key concept we have been learning about in calculus class in the past 3 weeks. Thanks to Dr. Drinen. The method we used was the Euler method. This method is comprised of a numerical procedure for solving simple differential equations with a given initial value. The method is named after Leonhard Euler, and who used it in his calculus book in 1768. This method is a foundation for many more complex methods in calculus. A differential equation is portrayed as a thought of formula where the slope of the tangent line to the curve can be calculated at any point on the curve.
In order to represent the graph we will show you in a few minutes, we chose gazelle and lions as gazelles are the prey and lions are the predators. And Chris here will explain how they relate to each other.
So, Ludfor said, I want to show you guys the relationship between the lion and the gazelle. So, as when the lion decreases, the gazelle population will increase because they will have less competition and more food and more population gazelle, so they will increase their population. But knowing that the gazelle will increase, then the lion will then increase because now they have the food resource, so they can have food and everything. But when the lion will increase, then their food resource will then increase. It's just a cycle, keep going until it will stay constant. And Michael's going to talk about the variables.
Alright, so for our equations, we used 4 different variables. We used P of t to represent the prey population. Q of t is the predator population. P prime of t is the change in prey population. Q prime of t is the change in predator population. And A, C, K, and M are the constants that we used. So in order to model our system, we used 4 different equations. Our first equation describes the interactions between the gazelle and the lion and how it affects the gazelle population. Our second equation describes the interactions between the gazelle and the lion, but this time it shows how the lion population is affected. P prime of t is the logistic model of how the prey population would increase or decrease in the absence of lions. And our fourth equation is an exponential model of how the lion population would decrease in the absence of the gazelle. So in order to get the 2 equations that we used to model our system, we had to combine our first and third equations and our second and fourth to represent the lion and gazelle populations. So this here is our graph of the lion and gazelle population. As you can see, as Chris described, the lion population, or the gazelle population decreases, which leads to a decrease in the lion population. That leads to an increase in the gazelle population, which then increases the lion population, which decreases the gazelle population, and that continues over and over again. But as you can see, the amplitudes between different graphs does get smaller and smaller, and eventually the populations do stable out to a point where there is little to no fluctuation in populations whatsoever. So now we'd like to demonstrate our model. So one of our constants for D represents the limitation of how much benefit the lions get from interactions with the gazelle. If we were to increase D by from 0.00001 to 0.00003, then that should increase the lion population, which it does. As you can see, the lion population has increased disgustingly.
All in all, we came to the conclusion that while there are relatively huge fluctuations in the population of lion gazelles, as time passed, the fluctuations became smaller and smaller, and they eventually flatlined, creating a stable ecosystem between lions and gazelles. Thank you.
Good morning. We will be discussing the murder mystery situation in which the room temperature is constantly changing, which affects the dead body's cooling temperature.
I'm Rachel, and my partner Bianca and I will be discussing Newton's law of cooling and Euler's method. So first, Newton's law of cooling states that an object changes temperature at a rate proportional to the difference between the temperature of the object and the environment the object is in. And we use the equation F prime of T equals K times F of T minus R to describe Newton's law of cooling. F of T is the body's temperature at time T. F prime of T is the rate of change of the body's temperature at time T. K is a constant representing the body as it cools, and R is a constantly changing room temperature. And in this graph, you can see is just an example. This could be for a cup of coffee, and you see at time 0, when it's first poured, it's 180 degrees. But as time goes on, 2 minutes later, it drops to about 110 degrees.
So we use Euler's method as well, and it's a numerical procedure for solving differential equations with an initial value. It approximates the slope for the given curve on the graph. So in this example, the blue line is the curved graph, and the green is using Euler's method with line segments. So it creates local linearity that connects multiple line segments, and with the differential equation, we can approximate how the values will change.
So this is the map for the equations that we put in.
So basically what we did, we built a machine in which a police officer can come and just add the temperature that they found the body. So if here in T, you can see how many hours have passed since the body was dead. So this is the equation that we use. T is the time in minutes, F of T is the body's temperature, and F prime of T is the rate in which the body temperature changes, and R is the environment temperature will change.
So at time 0, we have the temperature that they found the body at, and normal body temperature is 98.6, which is the straight line right here in the graph. So to find how long it's been since the person has passed, you can go back in time. And so for, if you found it at 80 degrees, it's been a very short time since it passed, but if you found it, let's say 69 degrees, and you can see that it's been a longer time. On this graph, it doesn't get to 98.6, but at 69 degrees, it's been about 5.5 hours since it happened. So for this machine, all you have to do is input the changing temperature for the room at each hour and the temperature that they found the body, and you can see how long it's been.
This concludes our presentation.